Okay, this is section 18.5, predicting spontaneity. Now what we're going to do is we're going to introduce a quantity called the Gibbs free energy. So I'm going to call G the Gibbs free energy. And then the related quantity that we'll use is delta G, which is the Gibbs free energy change. And just like with other changes, delta G would be G final minus G initial. Or, for a chemical reaction, G of the products minus G of the reactants. Okay? Gibbs free energy. We're going to define the Gibbs free energy in the following way. H minus Ts. And we'll define the Gibbs free energy change as delta H minus T delta S. Okay? So that equation right there is very useful for us, as it is related to the enthalpy change, delta H, and the entropy change, delta S. So for a system, we can calculate delta G by using delta H of the system and delta S of the system. Now, the significance of that is that, in a sense, this tells us or gives us the same information that we would if we were to use the equation we talked about in the previous section, which was delta S of the universe is equal to delta S of the system plus delta S of the surroundings. It turns out that it's more useful for us, or more convenient for us, to use this equation than it is to use this one over here. And the reason for that is that energy is easy to measure. Distributions of energy, or entropies, are not that easy to measure. So generally, we can measure the transfer of heat. That allows us to calculate delta G. Okay? So we're going to use this equation here, this Gibbs free energy change, delta H minus T delta S, in our calculations. Now, here's what ends up happening. If delta G is greater than 0, and what that means is it's positive, right? We will claim that this is a non-spontaneous process. If delta G is less than 0, meaning it's negative, it is a spontaneous process. And if delta G is actually equal to 0, right, it is 0, the system is at equilibrium. Okay? Now, this, in a sense, is the opposite of what we saw for this equation right here. What this said was that if the change in entropy of the universe increases, is positive, that would be spontaneous. But the energetics, the Gibbs free energy change, is the opposite notation. Essentially, if you want an analogy, imagine something falling. So if this ball falls, that's spontaneous, right? Something falling is spontaneous. Something jumping up, that's not spontaneous, right? That's non-spontaneous. So what's essentially happening in the first case, case 1 we'll call it, the spontaneous process, is the energy is decreasing. The potential energy is decreasing. Whereas in the second case, the potential energy is increasing. So potential energy, this process is non-spontaneous, meaning you have to put energy in for it to occur. It doesn't happen on its own under those conditions. That's essentially how we'll interpret the Gibbs free energy change. If the Gibbs free energy change for some process decreases, that's a spontaneous process. If it increases, it's a non-spontaneous process. Okay? So going uphill, that's non-spontaneous. Going downhill, that is spontaneous. Okay, the rest of it is really just sort of calculations and interpretations here. Let's take for one case, suppose we're at equilibrium. Suppose I say we're at equilibrium. Well, that would mean that delta G is equal to 0, right? And that's equal to delta H minus T delta S. So that means that delta H minus T delta S also has to be 0. Okay, so if I add T delta S to both sides, I get this relationship. Okay? And if I divide both sides by delta S, I get delta H over delta S. And so this essentially tells us the temperature at which a process becomes spontaneous. Right? Because if you're at 0, if delta G is 0, that's right where it's going to be spontaneous. If it increases a little bit, it becomes positive. That's non-spontaneous. If it decreases a little bit, that becomes spontaneous because it's negative. So the temperature at which that occurs would be this one right here. So you can tell, if you know the delta H for a process and you know the delta S for a process, you can find the temperature at which a process becomes spontaneous. There's a sample problem in your textbook which discusses that. Now, in terms of calculating delta G, there's different ways to do it, but one of the simpler ways is analogous to what you've done for delta H and delta S. Under standard conditions, the Gibbs free energy change for a chemical reaction is equal to the sum of the number of moles of a given product times the Gibbs free energy change of formation of that product. Again, under standard conditions. Remember, the degree sign means under standard conditions. Minus the sum of the number of moles of each reactant times the Gibbs free energy change for those reactants. So we calculate it, or can calculate it, exactly the same way we would do delta H of a reaction or delta S of a reaction. These are all listed in Appendix 2. Okay, very nice. It's a nice way to do it. There's other types of calculations we can do as well. We can look at phase changes, for example. Okay, so if, for example, we're looking at melting, or the reverse of that, freezing, or we're looking at vaporization, or the reverse of that, condensation, we're going to make the following claim. I'm going to take it as an example, melting. So let's imagine we have a solid here. And I'm going to use ice, which is really H2O solid, right? So suppose you have these ice molecules here, water molecules in the form of ice. And we raise the temperature to exactly 0 degrees C, which is 273 Kelvin, right? At that particular temperature, the substance is going to melt. And what happens is, if you're right at that point, the Gibbs free energy of the solid is actually equal to the Gibbs free energy of the liquid. Okay, they're equal. So liquid water molecules, which are more randomly distributed, right? So liquid, their free energies are equal to each other at that point. If you raise the temperature, the liquid has a lower Gibbs free energy. If you lower the temperature below 0, then the solid becomes more stable, and the Gibbs free energy of the solid is lower. than it is for the liquid. So what happens is when you're at one of these points, the melting or freezing point, so that's a temperature, right? This is typically TF. It's not really T freezing, it's T fusion, but you can think of it as T freezing. And then T vaporization or TB, boiling, for boiling something or condensing it. At those given temperatures, the free energy of both states are equal to each other. So if that's the case, delta G is equal to 0. And so again, 0 equals delta H minus T delta S. So if you happen to know this value here, which we often do, those can be measured. So for water, so for melting water, temperature equals 0 degrees C, which is 273 Kelvin. Delta H of fusion is 6.01 kilojoules per mole. Okay, so you know we can tabulate those values. So if we're at the melting point of water, delta G is equal to 0, delta H divided by T is equal to delta S. How did I get that? 0 equals delta H minus T delta S. Add T delta S to both sides, and then divide both sides by T. So this would be the fusion point, the freezing point of water, and this would be the heat of fusion, which would be right there. That allows you to measure the change in entropy for the water going from a solid to a liquid. Likewise, if you're talking about the vaporization of water, boiling water, that happens at 100 degrees C, right? Under 1 atmosphere pressure in any case. So that's 373 Kelvin. Well, delta H of vaporization is called. By the way, these are standards. So let me put those standards in there. This is vaporization, is 44 kilojoules per mole. So that means that if you wanted to find delta S for that process, it would be delta H of vaporization divided by the boiling point. So you could put in your 44 kilojoules per mole and divide that by your 373 Kelvin, and you would be able to figure out the entropy change for that process. Okay? Now, that's kind of cool. It allows you to make quite a few calculations involving changes. So try the sample problems for these, and you'll get a chance to see how this works.